Now that we are done with inverse trigonometric functions and the role they play to calculate certain integrals, we're going to take a look at another type of functions that will come handy to calculate integrals, namely hyperbolic functions. And they're really an analog of trigonometric functions, so in the next video we're also going to look at the inverse hyperbolic functions, just like we did for inverse trig functions. So the hyperbolic sine of x is defined as the half difference of e to the x and e to the negative x, while the hyperbolic cosine is defined as the half sum of e to the x and e to the negative x. So if we draw the graphs of these functions, for the graph of the hyperbolic sine, we take the half sum of e to the x and negative e to the negative x, and this is the graph we get. We get something that looks odd, defined on the real line, and with a range that seems to be the entire real line as well. And indeed, this is the case, that domain and range are the entire real line, and the function is odd, which can easily be checked by plugging negative x in the formula defining the hyperbolic sine. On the side of the hyperbolic cosine, now we have the half sum of e to the x and e to the negative x, and you see that we get this chain-shaped curve, which has a minimum for x equals 0, and this minimum is 1. So the domain is all the reals, but the range is only the reals greater or equal to 1. And the function this time is even, in other words, the y-axis is an axis of symmetry for the curve, and we can check that easily by plugging negative x in the formula and checking that we get the same thing. So why do we call this thing hyperbolic sine and cosine, just like for trig functions? What is in common for these functions with the sine and the cosine? For the trigonometric cosine and sine, one of the most famous identities is that cosine square plus sine square of the same angle is 1. Geometrically, that means that if you pick a point on the unit circle, whose equation is x squared plus y squared equal 1, then its coordinates are really of the form cosine t sine t for a certain angle t, which in this case is drawn on the picture. An analog for hyperbolic sine and cosine is that the square of the hyperbolic cosine minus the square of the hyperbolic sine of the same angle or argument is 1. So how do we check that? Well, if we take hyperbolic cosine square t minus hyperbolic sine square t, it's a difference of squares, right? It's of the form a squared minus b squared, so we can factor it as a minus b times a plus b. And then if we write out what hyperbolic cosine and hyperbolic sine are, we obtain this expression. So now if you look at the first parenthesis, you see that you have e to the t over 2 that cancels out with negative e to the t over 2, and on the other hand, e to the negative t over 2 plus e to the negative t over 2, in other words, just e to the negative t. Similarly, in the second parenthesis, we have e to the t over 2 plus e to the t over 2, that's e to the t, and then we have e to the negative t over 2 minus e to the negative t over 2, so this cancels out. So we end up with the product of e to the negative t with e to the t, so that's 1. What that means is that for a given t, the point of coordinates hyperbolic cosine t, hyperbolic sine of t is on the hyperbola of equation x squared minus y squared equal 1. So in that sense, it is an analog of the trigonometric functions, where this hyperbolic cosine and sine are the analog of the trigonometric cosine and sine, where the functions, or rather the points whose coordinates are these functions, live on the standard hyperbole instead of the standard unit circle. So this is the geometric situation, and that has other consequences that are analogs of trig identities. You know that for the usual cosine and sine, you have a number of trigonometric identities, and there usually are analogs for hyperbolic cosine and hyperbolic sine. So for instance, cosine of a sum of two angles is given by the product of the cosines of these angles minus the product of the sines of these angles. And the sine of a sum of two angles is sine times cosine plus cosine times sine, where you alternate the angles. There are analogs for hyperbolic cosine and hyperbolic sine, which are given this way. These are pretty much the same formula where you replace the trig functions by their hyperbolic analogs, except for the negative sign in the first formula on the trigonometric part, that is positive sign on the other side. To verify that is a routine exercise that I encourage you to do. Simply plug x plus y in the exponential definition of the hyperbolic cosine, for instance, and then do the standard algebra on your exponentials and check that you get what you have on the right hand side. Similarly, some of the most helpful formulas in standard trigonometry are the double angle formula. That states that the sine of twice an angle is 2 times the product of sine and cosine of that angle, and that the cosine of twice an angle is the difference of cosine square minus sine square of the angle, and that can also be written as 2 cosine square x minus 1 or 1 minus 2 sine square x. And we've seen that this can be useful in particular to calculate some integrals. Now we also have analogs on the hyperbolic side of things. The hyperbolic sine of 2x is also 2 hyperbolic sine times hyperbolic cosine of x. And the hyperbolic cosine of 2x is not the difference but the sum of the squares of hyperbolic cosine square of x and hyperbolic sine square of x. And again, this can be written as 2 hyperbolic cosine square minus 1 or 2 hyperbolic sine square plus 1. Now we can introduce analogs of the other trig functions. So we can have a hyperbolic tangent, which would be naturally the quotient of the hyperbolic sine by the hyperbolic cosine. An hyperbolic cotangent, which would be the reciprocal, in other words, the quotient of hyperbolic cosine by hyperbolic sine. An hyperbolic secant function, which is the reciprocal of the hyperbolic cosine. An hyperbolic cosecant function, reciprocal of the hyperbolic sine. And then we can start looking at the derivatives of this function, starting with the hyperbolic sine, which is defined as e to the x minus e to the negative x over 2. So when I differentiate that, I just get derivative of e to the x is e to the x, derivative of e to the negative x is negative e to the negative x. When I multiply by the negative sign in front, I obtain just e to the x plus e to the negative x over 2, which is the definition of the hyperbolic cosine. Similarly, if I differentiate a hyperbolic cosine starting from its definition, exponentials are easy to differentiate, and we obtain e to the x minus e to the negative x over 2, which is the definition of hyperbolic sine. So we obtain these basic derivatives of hyperbolic sine and hyperbolic cosine, and we get just a cofunction without having to worry about plus or minus. And of course, from that we can derive the derivatives for the other analogs of trig functions. For instance, the derivative of the hyperbolic tangent, I use the quotient rule, I get the derivative of hyperbolic sine, which is cosine, multiplied cosine cos h, right? Which is multiplied by the hyperbolic cosine again, so we get hyperbolic cosine square. Then we subtract the derivative of the bottom, so we subtract sine hx, and we multiply it by the top, so we get minus sine h square x. And all this is divided by the bottom squared. Because of the identity we've seen, telling us that the point of coordinate hyperbolic cosine t hyperbolic sine t lives on the standard hyperbola, we obtain 1 at the top. In other words, what we obtain is 1 over hyperbolic cosine squared, which we can write as just hyperbolic secant squared x. So we get really an analog of the formula for the derivative of the regular tangent. On the other hand, if we look at the first fraction and we split it, we get hyperbolic cosine squared over itself, that's 1, minus hyperbolic sine squared over hyperbolic cosine squared, and that's just the square of the hyperbolic tangent. So another way to write the same expression is 1 minus hyperbolic tangent squared. So that gives us a formula for the derivative of the hyperbolic tangent. Similarly, we can calculate the derivative of the hyperbolic secant, and we obtain, because we are differentiating 1 over cos hx, we obtain minus the derivative of this, which is sin hx over the square, and we can rewrite that as negative hyperbolic sine multiplied by hyperbolic secant squared. Just the same way, the derivative of the hyperbolic cosecant is negative the derivative of sin h, which is cosine h, divided by sin h squared, and we can write that as negative cosine hx multiplied by hyperbolic cosecant squared. And finally, we can proceed just like for the hyperbolic tangent for the hyperbolic cotangent. And this time at the top we obtain sin h squared minus cosine h squared of x. And because we found 1 for the opposite, so we have negative 1 here, and therefore we obtain negative hyperbolic cosecant squared. And that can be rewritten just by splitting the fraction as sin h squared over sin h squared, that's 1, minus cosine h squared over sin h squared, that's cotangent squared. So we can rewrite this expression as 1 minus hyperbolic cotangent squared of x. Now using this, we can use that to do some basic exercise of differentiating functions that are expressed in terms of these hyperbolic functions. So let's say, for instance, I want to differentiate f of x, which is the square of the hyperbolic sine of x. If I'm differentiating a square, this is really the square of a function, so I can use a chain rule. I'm going to get 2 times the function multiplied by its derivative, and therefore in this case I get 2 sin hx cosine hx. In the second case, I have the function f of t, which is the natural log of sin h of t. And of course that would only be defined for t positive when sin h is positive. And this is again a composite, right? We have the function sin h that is plugged inside the natural log. When we differentiate that, we obtain the derivative of the natural log evaluated at sin ht, so that's 1 over sin ht, but then we have to multiply by the derivative of the function inside, so we get cosine ht at the top. In other words, what we obtain is hyperbolic cotangent of t. In the third case, we plug the hyperbolic cosine inside the hyperbolic sine, so it's again a composite, so we use again the chain rule, get the derivative of the outside function, derivative of sin h, that's cosine h, evaluated at the inside function, that gives me cosine h of cosine hx, and then we have to multiply by the derivative of the function inside, so that gives us outside a sin hx. So this is what we obtain for the derivative of y. Again, number 4 is again a composite, and we have the hyperbolic tangent of 4x. So what I'm going to obtain is the derivative of the hyperbolic tangent. We've seen that it's the hyperbolic secant squared, evaluated at the function inside, so that will be evaluated at 4x. Then we have to multiply by the derivative of the function inside, so we have a 4 that pulls out. And we obtain 4 secant h squared of 4x. Finally, we want to differentiate the function u of t defined by the hyperbolic cotangent of square root of 1 plus t squared. So this is again a composite. I have the function square root of 1 plus t squared plugged inside the hyperbolic cotangent. So we get the derivative of hyperbolic cotangent, which is negative hyperbolic cosecant, evaluated at the function inside, and then I have to multiply by the derivative of the function inside. So just derivative of root of 1 plus t squared. This in turn is again a composite. I have the function 1 plus t squared plugged inside the square root function. So for the derivative, I get derivative of the square root function, that's 1 over 2 square root, evaluated at the function inside, so I get 1 over 2 square root of 1 plus t squared, and then I have to multiply by the derivative of 1 plus t squared, which is 2t. So I obtain this negative hyperbolic cosecant squared of root of 1 plus t squared, and this is multiplied by 2t over 2 root of 1 plus t squared. Simplifying the 2's, putting everything in one fraction, we obtain the opposite of t hyperbolic cosecant squared of root of 1 plus t squared divided by root of 1 plus t squared. Now turn to the next video where we're going to look into the inverse hyperbolic functions, which are going to be much more fundamental for us in terms of tools to calculate certain integrals.